Hi there.
Okay, yep.
We're calling in from Princeton.
Thank you for the kind introduction. I've been here at least one other time to give a department seminar, and this is building on that. Hopefully there's not too much repetition, but I doubt anyone would remember anyways. So today I'm going to talk about model complexity. Okay, and in particular, all right, first of all, let me get oriented here. This is pointer, maybe?
Yeah. You gotta hold down the,
There we go. All right. And then advanced slides, maybe? Okay, how do I advance the slides? Just, okay.
was this not working?
Well, I tried.
Yeah.
Which one did you hit?
Yep.
That's the same one I hit. All right, must be. All right, there we go. Okay. All right, so why do we care about phosphorus? I'm sure that I'm just preaching to the choir here, but just in case, phosphorus is an essential element. And thus, when we apply phosphorus to phosphorus deficient ecosystems, we see increases in crop productivity, crop yield. But this is only valid up to a point. This slide I actually got off the internet last night from the University of Minnesota. And what it shows is that as for A1P phosphorus test, so that's what they use out there. We use, I believe, Mehlich 3 for everything. Is as you increase the soil test phosphorus concentration, you are going to increase your grain yield, but at some point it flattens out. So obviously there'd be an economic incentive to reduce or stop once your soil test P gets to this level. Say, well, I don't need to. Why should I invest in fertilizer and apply it? But those of you who've worked with farmers, some people say, well, I don't care. I'm still going to add. But also from another perspective is when we're dealing with manure. You have to get rid of it. So you have to apply it somewhere. And you might be applying it to fields that are already up here, but what else are you going to do with it? So why we're concerned is that as the soil test P levels increase, this is data, this is actually from an ARS unit in Pennsylvania from the FD36 watershed. This slide, a few of these slides, I'll talk Deanna Osmond from North Carolina State, I've done a lot of this work with. So this shows that the crop response is going to be in this, low level here, around 50 ppm range. But as the Mehlich 3P continues to increase, you're not going to have an impact on the crop yield. But what happens is that the concentration of dissolved P in runoff is going to increase, sometimes linearly, sometimes non-linearly. But it becomes an issue. We also know that when you surface apply manure, which in my unit, that's where we're primarily focused on. This manure that's sitting on the surface during a runoff event or a rainfall event can end up in our waterways. And why do we care about that? Well, when these phosphorus-enriched waters end up in a phosphorus-sensitive water body, you can get accelerated eutrophication. And it's worth pointing out that, we're oftentimes focusing on the surface pathways, but also subsurface pathways. We know that historically we've always thought phosphorus isn't moving in the subsurface. It gets absorbed, it's not an issue. But we know now that that's not necessarily the case, depending on the soils. And also, what's becoming more common here in Kentucky and elsewhere are tile drain fields. So you have these tiles, they become these like point sources of pollution, if you will, and you're basically short-circuiting the natural filtering capacity of the soil. If the phosphorus would normally travel hundreds of feet, if not more, before discharging, it might only be a foot or two. So this, elevated phosphorus after eutrophication, low dissolved oxygen, fish kills, water aesthetics. You can just look at the difference here. Which would you rather be paddling on, which lake? So that's why we at ARS are concerned about this. So this response to phosphorus loading. So just to give you a brief history, in the late 90s, USDA, NRCS, and EPA developed a strategy for implementing nutrient management plans. With the idea is, if we help farmers, producers manage their nutrients better, the idea would be that less of this is going to be ending up in our waters. So NRCS revised their nutrient management conservation standard to include phosphorus-based planning. And essentially, they gave three options, states three options. You could base it on an agronomic soil test P. So basically, you would not apply phosphorus after you've met the plant's needs. Obviously, I don't think anyone has adopted that because that's very restrictive, right? What are you going to do with all your manure? Because as I was showing you before, we're talking like in levels 30, 40, 50 parts per million. And we know that it's not uncommon here in Kentucky to find soils 200, 300, 400 or above. You can have an environmental threshold soil test P where it's some multiple of the agronomic soil test P, the critical level, or a tool, a model that's called the Phosphorus Index. Depending how time goes, I don't know how much detail I'm going to get into, but it's 47 states have adopted the Phosphorus Index. It's a very simple model. Some would argue probably too simple. We've recently updated the one here in Kentucky, and again, hopefully I'll have time to talk a little bit about that. But recently, NRCS revised this 590 standard. I served on several committees that made recommendations to NRCS, and one of the things that we recommended that they include is if people are making judgments on whether you can restrict, and I should say that this is not by law. In most states, it's not a legal issue. It's only becomes an issue is if you're getting NRCS money. And if you're taking their money, then you have to follow their nutrient management plans. And if you're going to use the phosphorus index, well, you probably need to test the accuracy of it because you're making decisions on what gets funded, on how you're telling a producer to manage his or her land based on a tool that has very limited science behind it. So how would you evaluate a phosphorus index? Well, ideally, it'd be against measured data. You would have a bunch of sites, you'd look at the risk. So the idea of the phosphorus loss, the phosphorus index, is to evaluate the risk of phosphorus loss from that field, given your management conditions, crop you're growing, how you're managing the field. So ideally, we would have a bunch of fields, we collect runoff data, we'd look at our index and see if they correlated. Well, there's maybe a dozen studies out there in the literature that have done that. So a very limited amount of data. So what we had proposed through a lot of back and forth is, well, why don't we take a look at how our indices compare with these more process-based phosphorus loss models that were based on more data and in principle should be a better representation of what's going on in the field. Now, the advantage of this is you can run your models under a bunch of different conditions, get this predictions of phosphorus loss, take those same conditions and whatever parameters you include your index and put it in your index and see if your index is correlated with this more rigorous model. But the underlying assumption of that is that that model is actually truly a better predictor of phosphorus loss than your index. And surprisingly enough, we don't know that that's necessarily the case. Just because you have a bunch of really fancy equations does not necessarily mean that that's a better representation of reality, that you're capturing what's going on at the field scale. So NRCS funded 3 CIGs, really, and to look at, this is 4 years ago, Brad, would you say? To evaluate both commonly used phosphorus loss models and phosphorus indices. And we had 3 regions. The one I'm going to talk about is here, the southern region. And then there's this national synthesis project that kind of tried to tie this all together. So our objectives, first of all, were to identify sites. So part of this was not to collect new data, but is to identify existing locations where adequate data were available that we could use. One of the things that turned out to be a much bigger headache than we anticipated is taking the data and combining them into one database. You have data collected in different states by different researchers, different decades, and trying to get that combined together, and then going back to these people, say, some is published, some is not, some had rigorous QA/QC, some did not. And that's kind of on our lessons learned, is one of that, when you collect data. And one of the issues that we have in our field, and probably in others as well, is that the modelers and the experimentalists, the people who are out actually collecting the data and running the experiments, don't talk to each other. So the modelers, we're getting the data after they've collected, and we say, well, you really needed to measure this. And then they don't then the people who are collecting the data say, well, why can't you use what we've collected in your model? Well, because you didn't measure this parameter that they could have easily done. And one of the arguments that we made is we really need to get these people in the same room and talk about, before going out and collecting field data and running these experiments, talk to a modeler, say, what do you need from me? And how can we use this data to help develop and help improve your models? And even like QA/QC, when I got all this data and I went through, I couldn't believe some of the things that people weren't picking up on. When you have phosphorus loss data, 1 or 2 kilograms per hectare, and then you have one event where it's 86, and you just leave it in there. Well, go back in and you find out, oh, it was just a decimal point when they typed it in, but people aren't looking at that. So it's quite problematic. So what we want to do is, first of all, is compare some of these phosphorus loss models against its water quality data, and then the phosphorus indices against each other. And ultimately, the goal, which I'm not sure where the funding is going to lead, is to refine these phosphorus indices, like what we did in Kentucky, to be more consistent with the science. But also, one of the issues we have is you can have adjacent states running a phosphorus index, and where let's say you take the same field, right, and there's a state line right down the middle. One index might say you can't apply anything, and the other can say you can apply nitrogen-based, manure at nitrogen-based rates. So you're way over applying phosphorus, and that's obviously an issue, but it's more political than scientific, and that's a whole nother. That's a realm that makes less sense. So we were able to identify these sites. So you can see it's a pretty broad range in the south. Unfortunately, none up here, but Brad's going to change that, right? But just to give you an idea, pretty wide range. So plot sizes, small scale. The largest one were the Mississippi, were up to 17 hectares in Oklahoma. But field slope, a pretty good range. Soil test P, a pretty good range. Runoff from these fields. So obviously we wanted to get the most diverse data set with what we had at hand. So that just kind of gives you a range. And then I guess, let me see if I can go back here. And the amount of phosphorus loss. So the total phosphorus loss ranging from less than 1 kilogram per hectare all the way up to 11 kilograms per hectare, right? No, this one, yeah. No, this one here is 13, but you get the point. So as I talk about models, I think it's a good idea to get us all on the same page, at least you guys getting on my page on how I view models. And when I talk about certain things, what I mean. So first of all, we have to recognize a model is a simplification of reality. Thus, it's going to have some errors associated with it. you know, if it was the entire system, it wouldn't be a model, it'd be the entire system. So we're simplifying things. Let's just be honest with that. So to do that, we're going to cut some things out. We're going to assume some things aren't that important. You know, people ask, why are there so many models? If you could, we could sit here probably in 5 minutes and name at least a dozen models that have been developed for phosphorus loss at the field or watershed scale. Wouldn't be hard to do. So why are there so many? Well, in some cases, it's, I think, you know, legitimate differences on how we perceive what's going on in the important processes. You know, some models might specifically account for macropore flow, others might not. You know, those are two distinct differences. And if you're developing a model where you had a lot of fractured bedrock as opposed to, you know, a glacial till, you know, you probably are looking at different processes that you want to measure. But even if you agree that, let's say, matrix flow is important, you might describe that using different equations. So a more process-based might use the Richards equations, whereas another model developer might use a water balance approach. You know, which one's better? Well, they will argue that their approach is the best, but it really depends on what is it you're trying to do and the amount of data you have available to test your model. So I'm going to be talking a fair amount about process-based and empirical. So what we mean by this is a process-based equation model is one that tries to capture the processes within the governing equations, where empirical would be more along the lines, let's say, a regression equation, where you're just trying to correlate your phosphorus loss with things at the field scale, land management practices, physiographic properties, etc. And you're not necessarily interested in why that correlation exists. You just want to know that that correlation does exist and can be used to predict in the future. But in reality, you know, all models are going to have some amount of empiricism in them. Even the quote-unquote process-based are making some simplifications. They're not solving equations down, you know, the Navier-Stokes equation or anything like that. It's still empirical to some extent. But one of the advantages, theoretical advantages of process-based is you should be able to take, if you're really capturing the processes involved, the physics, the chemistry, the biology, that model should, in theory, be more applicable elsewhere. It should be more transferable than if you have just a regression equation set of empirical that really are going to only be valid for the conditions in which you develop the model. You know, lump versus distributed, you know, are depending on the scale you're looking at, are you going to assume that soil test P level that you measured is representative of the entire area, or are you going to break your field up or your watershed up and have different values for that? Static versus dynamic. So the phosphorus index is done on an annual or, you know, 2 or 3 year basis. One of the models I'm going to talk about today is an annual. But a dynamic, you know, these more complex models are going to be daily or hourly. You're going to need a lot more data for that. And one of the questions what we had is, when you think about it, so you apply phosphorus, especially if you're fertilizer, manure, and it's on the surface, one of the things that's going to really factor in how much is lost is what is the time between application and your first rainfall event? You can't really capture that directly in an annual model, but you can in a dynamic model. You know, the scale that we talked about, you know, deterministic versus stochastic. Most models, you put in a set of variables, inputs, and you get a single output for that. Stochastic, you're going to account for the uncertainty. So you might put in your certain variables, and either you directly or the model makes assumptions that you have a certain amount of uncertainty there. So your predictions aren't a single point, but it's a range of values, which I think is much more realistic, but much harder to do, and thus not done as often as it should be. And models are often used to evaluate the effectiveness of best management practices. So it's used in, you might run a model and someone who has a pot of money saying, I want to do this practice at this location is going to be based on what a model says. not on data or anything else. So there's really practical reasons for us to get these models right. So how complex does a model need to be? Now, for it to be effective, I would argue it needs to be reasonably accurate. I should have highlighted reasonably. Because people tend to think model has to be absolutely just straight on, just perfectly accurate, which is ridiculous. And so then we set ourselves up for failure. Reasonably accurate means there's sometimes we're going to get it wrong, way wrong. And we have to be okay with that and say, as long as it doesn't happen very often, we can accept that model. However, to be useful, it must be accessible. You can imagine a model that requires 100 different parameters and 10 years of schooling to run. It might be really, really accurate, but who's going to use it? If we're looking at on the farm scale, and we're looking at nutrient management planning, we need to have models which do not require a PhD to run. And that can't be said for a lot of the existing models out there. So I like to say modeling beauty is in the eye of the beholder. So we have this kind of a continuum. On one side, you accept the results blind faith. Well, my model said if I do this, this is going to happen. And that's it. That's end of story. On the other end is complete cynicism. I don't believe, I don't care what your model says. It's wrong. We know it's wrong. You made these simplifications. You made these assumptions. And any model, any environmental model, I can sit there and I can pick away at it and get most of the audience to say, that's useless. But is it really? Is it really useless because it has some significant flaws? I would argue the place to be is the skeptical believer. Trust but verify. And going to a quote that I think has been attributed to George Box, the great statistician. All models are wrong, but some are useful. We know that the models are not entirely correct. That does not mean they cannot help us and that they're not useful. So that's kind of like my mantra. Yeah, you can, when I show up, when I show this stuff, you guys can easily point out some flaws in it. So you're absolutely right. But that doesn't mean that we throw the baby out with the bathwater. All right, so what we wanted to look at here was first is comparing the annual phosphorus loss estimator. This is a spreadsheet model developed by a colleague of mine at ARS in Wisconsin. And it's done in Microsoft Excel. You type in a few parameters, soil test P, annual rainfall, runoff, and it will give you a prediction of field scale phosphorus loss. The biggest problem with it is it does not calculate runoff and erosion. But it actually, in this model, in this comparison, that was a good thing because we took the runoff that was predicted by this model and used it in here. So therefore, we were removing, if we were comparing two models that were also predicting different runoff and erosion, we wouldn't know why their results were different. But this is an empirically based model. And we compared it with a TBET, which anyone here familiar with a SWOT model, soil water assessment tool? That's almost, I hate to use the gold standard, but within the ag community and within ARS, it kind of is. And this TBET is supposed to be a simplified interface to this model, and it was developed specifically for Texas and Oklahoma. But it requires a significant amount of data and expertise to run, even though it's easier than SWOT. But it has some significant limitations. So what we want to do is compare these two models and see, is it worth putting all this time and investment in this when you can use a simple spreadsheet model to get similar results? So then that's what our data, first we wanted to compare the models to each other, and then look at actual observations of phosphorus loss. So from the different sites I was telling you, you can see here, Apple predicted dissolved P is on the X, and TBET predicted dissolved P is on the Y. Now, you can see these are log scales. So you know, that's a lot of difference. There can be a lot of difference there. And here's the residual. So the difference between T-bet and Apple, you do see that as the Apple predicted dissolved P loss increases, generally, this is the difference between the two models increase. And you can see overall that within these negative residuals means that the Apple predictions are consistently greater than those from T-bet. Now, if we look at just kind of statistics, there's a very strong overall correlation between the two models. The model efficiency, which is really just a measure of how well the two data sets fall on a one-to-one line. So if they're perfect correlation and they're predicting the exact same thing, you get a model efficiency of 1. If it's less than 0, what you're saying is that you can take the average of your data, and that'd be a better predictor than what the model's predicting. So as this percent bias is just a difference between the two, the average difference. And again, as you can see, Apple is consistently predicting higher phosphorus losses. So why? One of the things we want to look at is, all right, if there's a difference, can we explain it? Well, one is there's a difference in the extraction coefficient. So we know that in both models, one of the phosphorus loss pathways is what's coming off the soil. So you have some soil test p-value, you have an extraction coefficient in the runoff. We're using the same runoff value, we're using the same soil test p-value, but the extraction coefficients are a little different, but not enough to explain the differences we observed. One of the things that in the T-bet and really in most SWOT models, there's so many out there, has assumed until just recently is that when you apply phosphorus to the soil, it immediately partitions that phosphorus into the soil. Okay, so what that's going to do, even if you don't incorporate it into the soil, so it's going to instantaneously move some of that phosphorus that's sitting on the surface into the soil, absorb. So you're going to have less, the pool is going to be less. So that's consistent. If you're underestimating the amount of phosphorus available for runoff, why T-bet is under predicting compared to Apple. So I think, you know, we pointed that limitation out. And Apple, on the other hand, even though it's empirical, does specifically account for phosphorus that remains on the soil surface and is vulnerable to loss during a runoff event. And again, you know, it's also hard to really understand what is the effect of the different time steps. As far as looking at annual and daily and how that is going to affect how the model predicts phosphorus loss. But in general, what we can say is if you're using the Apple model, certainly in a management perspective, you're likely to result in greater predicted risk than T-bet. So this could be kind of problematic. If you're looking for a model, if you just looked at this and you said, well, I want to reduce my perceived risk, not necessarily if it's risk at all, but if I'm getting money from someone, if I want to show, I would then take T-bet and run it on my farm and say, look, because if I run Apple, it might put me above a certain threshold, T-bet might be below. So this kind of shows you, using different models, you might get different answers and different management. Now, what about particulate P loss? So this is just phosphorus that's attached to eroded sediment. And now, if you notice the difference, again, they're following along this one-to-one line, but now the data are all on to the left of the line. They're above this. So T-bet now is predicting greater losses than Apple for particulate P loss. Again, you see a strong correlation. Model efficiency is pretty good, but now the bias is in a different direction and even greater magnitude, basically a doubling. Before the all sites combined was like a -40 some. So again, even though it's well correlated, you're going to get potentially significantly different predictions. They use similar equations for calculating particulate P loss. T-bet does not include labile P. This is only for those who, I don't want to really get into details here, but if you're familiar with these equations, T-bet doesn't include labile P concentration when it calculates total soil P, which is how the particulate P loss is calculated. But that's just going to be a fraction of total soil P. So that's really not going to be that important. But it comes down here is there's this enrichment ratio. And the idea is that eroded sediment is going to be enriched in phosphorus, because it's going to be, when you take the bulk soil, what gets eroded? It's the finer materials. The finer material has greater surface area and likely is going to have greater phosphorus concentration. So it's going to be enriched to the background, the bulk soil. Well, in those equations, you put in the erosion rate, and the annual erosion rate as opposed to an event-based erosion rate is going to be different. And now if you're using Apple and your primary, if erosion, particulate P loss is the dominant pathway, now maybe using Apple is going to give you a lower predicted risk than T-bet. So completely flip depending on what's the most dominant pathway of loss. So one of the things that we're interested in, oftentimes when you're looking at models, you just want to see how well they predict. And you'll see on the x-axis observed, y-axis model predicted, and you hope it all falls on a one-to-one line. But in the context of nutrient management planning, and I think this might be a direction that modeling in general should go, is what about categorizing the fields? Meaning, in the 590 standard, you can apply phosphorus at different rates depending on the risk. We talked about that, the index getting a risk. Well, this is, and I need to stress, this was suggested by NRCS, these numbers. It's not written in fact, I think they got enough blowback on this. I don't think you can find this document online anymore. But as an example, and we've used this in several papers, but what they had said is, all right, let's say measured P loss, we would consider it low risk if it's less than 2 pounds per acre, or 2.2 kilograms P per hectare. And then medium risk, so at low risk, you can apply at nitrogen-based rates, meaning you're going to be overapplying phosphorus for most crops. At medium or moderate, you might be able to apply, depending on the state, apply at phosphorus removal rates. So that means you're going to be underapplying nitrogen, you'll have to add additional nitrogen. And then at high, you might not be able to apply phosphorus at all. So what we want to look at, all right, if we classify those model predictions using that classification scheme, what we're looking at is basically on this diagonal, right? Low, low, medium, medium. They're classifying the fields in the same way. And we find that they assign the same risk to 69% of the fields for dissolved P and 71% of the fields for particulate P. So again, this is one of those decisions. All right, they're similar. I think there's some good correlations. The Apple model is much easier to use. And as far as time and investment, so can you use this? Well, so far all I've done is shown what the two models predict. Ultimately we want to say, well, that's great. Maybe they're just 100% they're predicting the same thing, but maybe they're both completely wrong. So how do these models hold up with actually observed phosphorus loss? So we have Apple predictions on the left, T-bet on the right. You can see kind of falling on that one-to-one line if you're feeling very generous. Again, the residuals, I'm a big residuals. I think that when you go back, I guess I'll get on my soapbox. Just looking at that is certainly part of an analysis, but you really want to look at your residuals as well and look for trends. But you can kind of see a general trend. They certainly are similar, but take a look at the magnitude of those residuals on some of them. pretty significant, right? And if we look at our goodness of fit statistics, now we see a correlation for the two models. I mean, I think that's okay. The model efficiency, if you look at, certainly in hydrology, we're right on the borderline of what's considered an acceptable model. So I don't know if I'd call it acceptable, but not horrible, not zero, not negative. But look at this. This is a median absolute percent error. So the median value between the observed and the predicted, 81 and 71%. So that's pretty significant. So any model prediction you have on average, or the median, is going to be off by that percentage. The bias, again, so Apple is going to overpredict this dissolved P, and T-BAT's going to underpredict it. But the root mean square error, so your average error, right, is over 2 kilograms per hectare. And if you're talking about phosphorus loss in the range of 2, 4, 6 kilograms per hectare, that's pretty significant. Similar correlations, model efficiency, similar. So again, both models had high median absolute percent error and root mean squared error. Now, what about total phosphorus loss? Well, again, we see, you look at that, you can see that they seem to be pretty similar. A whole lot of unexplained variability, though, right? Now, looking at the residuals, still there, you can still see a general trend as these predictions are increasing. The difference between the observed and the predicted increases. Now we see a correlation of 0.57, 0.52, yes, statistically significant at the 0.001 level. But look at the model efficiency. Both of them are less than 0. So if you were to give me that data set, I could make a better prediction of all those data points by taking the average value than the model did. Now you might say, well, if you're predicting the future, you don't have the average data. That's true, but I think what it's saying is the model is not really doing a particularly good job. The median absolute percent error, you can see, is pretty high. The root mean square error is even higher for this. Again, so the question becomes, whoops. So both models generally underpredicted total phosphorus loss. So why? Both of these models, if you look in the literature, have been shown. You can look at, let's stick with the Nash-Sutcliffe model efficiency. You look at, there's several papers that have shown that number to be greater than 0.7 on field scale, like what we did here. So why such a poor correlation with this existing data set? Well, one of the things what we wanted to do is what I would call a truly predictive mode. We took these models and ran them without calibrating, without doing any fitting to the data. And as a result, we used uncalibrated runoff and erosion. Okay, so what does that mean? Well, to calculate runoff, you need certain parameters. Let's say we were using the curve number method. So you need certain properties, land, the soil type, the land use, and then you can get a curve number from that. Well, usually what's done is you run the model and you let the model select that curve number that best describes your data. But in reality, that's not going to happen if you're truly predictive. So what we found is doing that. In this case, we did not calibrate runoff and erosion. And what we found is our model efficiency, for all sites, the runoff wasn't too bad, 0.47, but erosion, we were doing a poor job predicting erosion, or the T-BAT was. A very poor job. And if you remember, the dissolved P, the model efficiency was adequate, okay? We were getting the dissolved P pretty well, I mean, reasonably speaking. But the erosion, we were way off, or the particulate P loss, the total P loss. And that's because our predictions of erosion were way off. So what we were able to do, so with Apple, because it does not calculate runoff and erosion, but it's a model input, what we then wanted to test is, all right, let's take the measured runoff and erosion. So that would be a perfect model prediction, right? And put it in and see if we can improve. And in fact, so overall, the dissolved P, we see a somewhat improvement, but total P, we go from minus 0.13 to 0.43. But look at a couple of these sites. The Arkansas site from negative 0.52 to 0.35. Even though these are negative, you can see that they're getting less negative. But the total P, Arkansas minus 0.76 to 0.39. This Texas minus 0.1 to 0.78. So and I think we know this, but what this clearly shows is that if you can have the best P cycling routine you want, but if you're not predicting erosion and runoff well, I mean, think about it. I mean, it's common sense, but oftentimes we have to go through these great exercises to point out the obvious, is we're not going to predict phosphorus loading that well. So, maybe, we need to spend time improving our phosphorus cycling models, no question. But maybe we really need to be focusing on improving some of these equations, these models that have not been modified for decades on predicting runoff and erosion at the field scale. If we wanted to take a look at the classifications again, so again, the diagonal means using that classification that the model and observed data classified them the same. So that's dissolved P, total P. If you look at it, about 70, so 76 and 81% of the fields were properly classified using the thresholds we used for dissolved P loss, but only 54 and 62% of the fields for total P loss. But again, one thing I want to stress is the similarity between the two models. You're not gaining a whole lot, significant improvement by using a much more complex model. If you just do an ordinal correlation for ordinal data, you see that, again, they're very similar between the two. And for any of you who are into weather, I think this is primarily used in weather forecasting, but it's a Heidke skill score. And basically what it tries to account for is perfect forecast yields a score of 1, and it accounts for categorizations, ratings that would come about strictly due by chance, and it pulls those out. And again, so the closer to 1, the better. But I think the important part is you see that the values for the two models are pretty similar. So the model predictions were strongly correlated. We do know that Apple's going to generally predict greater dissolved P losses than Tibet, and conversely, Tibet's going to generally predict higher particulate P losses than Apple. So depending on which is the dominant pathway, that's how it'll impact total phosphorus loss. Both models provided, again, I think the people who developed these models will say I'm being too harsh. Maybe I am. I would say it's relatively poor predictions. I think it's due in large part to the poor predictions of runoff and erosion. But both models provided similar categorizations of P loss risk in nutrient management context. And again, so I think making the argument that how complicated of a model do we need, given all the other uncertainties? If we can get similar predictions on a spreadsheet that I can sit down and run a set of fields in a couple hours, and it takes my colleague 3 months to run the same number of fields, so is use of complex models justified? Well, it really depends on the question you're asking. But in a nutrient management planning context, maybe we can go simple. So real quick, the next part of this study, I talked a little bit about the phosphorus index. So now we're looking at the models, and we show that the models, the accuracy is debatable. But how do the predictions, what about a phosphorus index? let's see. So the phosphorus index, was proposed years ago, literally on the back of an envelope. You hear things about back of the envelope. My understanding, I don't know how true this is. This could be an urban myth, is that this was first developed at a bar on the back of a cocktail napkin. A couple guys sitting around saying, what would be important to include? The phosphorus index has come under a lot of criticism. They've been developed based on professional judgment rather than scientific data. NRCS made these proposed this kind of approach, no money. If you talk to the people here at UK who were involved in the original index development, and that's what they say. We were told we needed to get something, design something, but there's no money, so people have to get funded. Huge amount of diversity, and I talked about that before. You can have a field that straddles a state line and have completely different, if you have a proposed method of amount of manure to apply, one side might say apply all you want, another say you can't even get on that field. So that's a legitimate criticism. Some arguments have been perceived as the index is too farmer friendly. So there was a push 6 to 8 years ago to just get rid of the index and go strictly on a soil test P level. If you're above a certain level, you can't apply. So many of us were saying, well, no, that's, if the transport is low, you can have a field that's high in soil test P, but if there's no runoff, there's really no leaching, is it really risk? You can have another place that has really low soil test P levels, but there's a lot of runoff, a lot of erosion, and that loading from that area is actually going to be greater. So we really need to account for the transport. So that's when we got involved in all these grants and committees and trying to jump up and down, say, we need to do something. But, so this is where we said, let's at least take a look at our index and see if we can improve it. So what would an index look like? This is the original Kentucky index, phosphorus index. And so you can see each factor has a certain weight, and depending on how it's rated, you get a certain number of points. So if you're a planner, you'd have a field and you'd say, all right, you'd look at your soil survey and say that you have the hydrologic soil group is C, your soil test P level. So you would go through all this and then you would calculate this out. So this is 4 points times the weight, which is 1. This is 2 times 3 is 6. You add that up and you get a level, and then your value, and then that value would tell you whether you can, what you have to do if you're limited. Now, just looking at that, you might say, well, I can see why those parameters, those field characteristics are included, but where did these weighting factors come from? Do those seem reasonable? What about the value up here? It's very rule of thumb, if you will. So I was fortunate enough to be involved in an effort to improve, change it, modify it. And my argument has always been, let's get the most scientifically defensible index. And then if it is overly restrictive, then let's make arguments from a different perspective. But don't base it on what some tool that is not based on available data. So I'm not going to get into details here, but just to show that it's a little more rigorous than the other one. And it's really based a lot on those equations that are in that Apple model. So what we did is then we took, so we had that runoff data that we compared the models with. Then we ran the indices for these states, for these fields, and this is just for the North Carolina. We did this for all 11 sites. But just to give you an idea, so here's what the measured loss was, and then the NRCS rating, what their proposed or suggested thresholds would be, and then what each index assigned it as. Okay, so 51% of the state ratings corresponded to what NRCS would have rated, what the observed value was. And when a state index was wrong, it generally over predicted the risk. So if we look at all, kind of tying this all together, this is the percent correspondence with the NRCS loss rating, okay? So here's the Apple model, the TBET model, like we said before, similar, okay? Apex is even more complex to use than TBET. Now, the phosphorus indices have three general formulations. One is additive, like the original Kentucky index, where you just have these different parameters, you add them up together, and you come up. But it's missing interaction terms. I've argued, and I think I've shown that this component index, which is how we design our models, where we have a source and a transport mechanism combined for each pathway. The multiplicative approach is kind of in between. It takes a transport over here and then the source over here. You multiply the two together and then, or add them separately, get numbers for each one, then multiply the two together. And there's some theoretical problems with that. But in any case, you can see that all the states that had a component index actually categorized the fields better than any of the models. And the multiplicative was similar to the component, and then the additive, which I'm not surprised, came in last. But again, if we're looking at complexity and just how much is left unknown, you know, these data show that even the simple phosphorus index might be adequate for a lot of what we're doing. I don't think there's anything there that I haven't already covered. Leave some time. So I just want to recognize my collaborators. Adam Forsberg did most of he was a student under Dave Radcliffe at University of Georgia. He did most of the TBET modeling. Aaron Middlestedt, under the guidance of his advisor, Daniel Storm, did most of they both did the TBET modeling. Adam did it in in 3 or 4 of the states, and Aaron in the other. And Dan Osmond and Andrew Sharpley were kind of the leaders in this effort over the last few years. So with that, I will take any questions. Yes?
So for some of these correlations that you showed between the two different models, some of the states were kind of consistently up to maximum.
Yeah.
So did it help, or did you guys try to eliminate or exclude them for the sake of comparison for that time?
What we try to do is look at why was that different? So one of the things what we want to do is, all right, we can show differences, but why? And will that help us improve the models? So in looking at, and also one of them, like Mississippi, there's only 4 data points. So that can be really, you know, if you look at a model efficiency or a correlation, 4 data points really. But if in one of the, and I forget one of the states, one of the models was really much higher than the other one. But that state, those sites had a lot of manure applied. And one of the biggest difference between the models is how they handle applied manure. So we were able to kind of look and make some, I believe, reasonable recommendations on how to improve the one that we thought was less adequate. But looking at the different states, so what we want to do is, all right, where these models really diverge, what is it about that? Is it more erosion? Does it correlate with high erosion? Does it correlate with high soil test P? And really trying to get down to why those are different. But we didn't pull any out. But you know, we could, if we pulled out a few, yeah, the overall correlation could improve.
Yeah, I mean, maybe to take out all the excluded ones and try to look at these together, maybe they can have something to come out.
Right. Yeah, and look at maybe if you took some type of a threshold on a model efficiency, these we're going to say are good. So let's look at what do they have in common, and then the ones that are, yeah, that's a good point. we took a look at the bad ones, but we didn't really take a look at the good ones.
Carl, is it
Yeah.
likely that any of these indices and models will ever be used as the basis for regulations?
Well, I'm not the person to ask, and I'm certainly not when it's something when it's going to be recorded. But you know, I don't. There's always this fear that at some point the carrot's not working, the stick's going to have to be used. But you know, certainly in the current political environment, probably not. You know, I think certainly ideally we'd all agree it'd be great if we could get to where we need to be without more rules and regulations. But how do you get there? I don't know. Josh is going to actually clear this up for us.
Well, I was going to say, there are places where it is.
Yeah.
P-index regulatory in Maryland, Pennsylvania, to some extent. So, I mean,
Basically anything in the Chesapeake Bay watershed. Yeah.
Yeah, but it's definitely firmly regulatory in Maryland. But so my question relates to that. You know, and you and I have talked about this a lot. So, but you know, your point of looking at the precision, the error around the components of these models of these indexes. And Pete and I have kind of debated, you know, why don't you just use it like in Maryland? Why didn't we just use Apple instead of using Apple to calibrate an index?
Right.
And my argument, where I look at it instead from the soil mechanism, from a the management mechanism, strings and management control process runoff, so an index allows you to weight management activities based on their downside potential. So that precision, like if there's a management activity that has bigger error bars, means you have bigger. When things go wrong and it doesn't behave to the mean, there's much more impact on water quality when it's off the mean. So that variability is important. An index you can account for the weighting of that.
Right.
So what do you think about that as far as using that precision, the size of that error bar to weight the components in your index versus sort of model?
Well, I think you could do that in the model as well. But I think, you know, one of the things too we forget is using the indexes. We want to educate people. We talked about this on our way to lunch. Is if you have a really simple tool and the farmer can put in the different parameters and see, wow, that's really going to change my risk of loss. And then they start to understand, well, you know, maybe I shouldn't be applying near the stream. But with a model and it's doing all these equations, they're not going to get that correlation. You know, they're not going to understand why they're getting a high number. It's plug and chug. With an index, you know, very simple, and you can go through, and I think that it shows what it is you're doing that's causing that high number. But you're right, as far as with the index, it's much easier to put in some management factor. And you can, if you want to encourage a certain management, then you put a high weight on that or a low weight, depending on, you know, which direction you're going. And that would encourage, when they run the numbers, they would see a significant reduction in their risk if they did BMPA as opposed to BMPB. So you could use that to encourage certain behavior. Yeah, and you know, I think, but we haven't done a good job with that. And we also haven't done a good job in saying, this is just an estimate of your risk, right? Yes.
So you mentioned about recycling the model.
Mm-hmm.
What do you think, like, on the recycling model, incorporate that's one of the important factors.
Right.
So you have a cycling model incorporated in this model that you predict.
Yeah, but then you start getting away. The purpose of the P-index is something really simple, that you start incorporating soil or phosphorus cycling. Now you need additional parameters. How do you get those parameters? Is that reasonable? And you got to look at correlations between something that you can get off a soil survey. And you can do that, and Apple is based on that. So there are equations for the phosphorus cycling. One of the parameters that's needed is the phosphorus absorption parameter, or capacity parameter. Well, there are equations out there that show that it's related to clay content, your soil test p-value. So you can use that and incorporate that. But it's just this, the tension is, all right, you have an index, and we pull that index, and you could say, yeah, I think that we could do a better job when we had the phosphorus cycling routine. Okay, well, we can do a better job when we had this. Where do you stop? And next thing you know, you have a model, a more process-based model. And what we're showing here is, if you have a decent phosphorus index, maybe that's as good as you're gonna get for what we have now. How complex do we need to go? But again, it depends on the question you're asking and what it's being used for. But yeah, no, I think that is a good point. Yeah, Josh.
So you just said something that you said if you have a decent phosphorus index, that's good. Yeah.
I said maybe.
Yeah, maybe. Okay, so in 2 weeks or 3 weeks or something, you're going to be on the phone telling NRCS about this work, right?
Yep.
My question would be is then how do you encourage states to adopt the DCP index? Because a lot of them got crappy index.
Right.
And the people in charge of them, good friends of ours, are just like, man, there's no political motivation to get involved
Right.
in this, so we're going to stick with our crap.
Yep.
Including Kentucky, we've got 2 indexes, right? So.
Yeah, that's the one issue. We could make a perfect phosphorus index, but if no one's using it, what's the point? And that's been one. I don't know. I mean, the best, I went around for years before we even moved forward here. I went Kentucky Farm Bureau, I've been here, I've been everywhere saying, the original index, we can do better, we can do better. Everybody would say yes, then they would leave. And then, that was it. So how do we get people to care enough to say, and like you said, some of the states that we showed, but you contact them, they say, yeah, but who do you contact? There's no person, no department that has taken ownership of it. So it's done 20, 25 years ago.
So I would argue that at least the person that, if the land grant university holds the index, in most states does,
Right.
that person should take enough pride in their job to have it.
Yeah.
Is what I would argue.
Well, bring that up on that conference call.
I will.
I want to check with Princeton.
Okay. So Princeton, do you have any questions?
No, we don't. Thanks.
Anything else for Carl?
I think there's only one person there. So.
Let's thank him again for a great time.